Okay, we're going to look at some extra examples on the 3-4 section, which deals with the horizontal and oblique asymptotes. Horizontal asymptotes, kind of like a vertical asymptote, it's just what happens to the graph as it goes off to infinity. So if I have a horizontal asymptote here, it looks like this horizontal line. Well, then what you'll see is the graph will kind of approach it somehow, something like this, from both sides. So that's a horizontal asymptote. Now, it's a pretty easy way to find it. It's all based on the degree. If the degree is bigger on the bottom, then you automatically have a horizontal asymptote of 0. So the horizontal asymptote is always y equals 0 if the degree in the denominator is bigger than the degree in the numerator. If the degrees are equal, that's when we divide the leading terms. And we'll see some examples of what that looks like. So in this first case, this first example, you notice that it says 3x7 on top, so this is degree 7 and this is degree 9. Now, since the bottom is 0, you automatically have a horizontal asymptote of 0. Now, in this case, the second one, 6x squared plus 3x plus 2 over 3x squared minus 4x plus 1, you notice the degrees are the same. So, like it says above, we're going to take the quotient of the leading terms, which is 6x squared and 3x squared. So, if I want my horizontal asymptote, it's going to be y equals 6x squared over 3x squared. So the x squareds cancel. 6 divided by 3 is y equals 2. Now this final one, if you look, it says we have x cubed on the top. So our leading term up here is x cubed. And on the bottom is also x cubed. So I'll just divide these leading terms. So my horizontal asymptote is going to be y equals x cubed over 7x cubed. These will cancel and just give me 1/7. So what you would expect to see with this graph, now I don't know what this graph looks like at all, I haven't graphed it, but if I have an asymptote at 1/7, this graph somehow is going to approach this asymptote. Now in this case I have it coming from the top and bottom. It could just as easily come from this way and this way, or it could come from both on the top or both on the bottom, just depending on what it looks like. Desmos does a great job because you can see how it flattens off as you go out to infinity. Now, the one case we didn't talk about was if the numerator had a higher degree than the denominator. And if we do have that, then we have what's called a slant asymptote. Now, a slant asymptote is when you have some graph and you have some slanted line, and the graph somehow, as it goes off, it approaches this slanted line from both sides. So as you get to bigger values of x, the graph sort of makes this diagonal line on both sides. So to find slant asymptotes, and again, this is only when the degree of the numerator is bigger than the degree of the denominator. Honestly, it is a lot more work because you actually have to do your long division. Now, we're getting long division, but remember, we just want to get a linear function. So to do long division, I'll do the bottom, and then I'll divide that into the top. Now, we don't have to do the whole division because I just have to go until I get my line. So if I look at this, I'll look at the first terms, because if you remember long division from Algebra 2, we'll take 3x to the 4th divided by x cubed, which cancels all but 1x, so that's 3x. And then I would multiply that to all 4 terms here. So that gives me 3x to the 4th minus 3x cubed plus 0x squared minus 12x. Now the trickiest thing with division is at this step we have to subtract. So we will change all these signs to the opposite. And what that'll do is it'll cancel out this one, it'll cancel out this one, it'll give us negative x squared and plus 13x. But I'm actually done now, because if I try to divide again, if I try to divide negative x squared divided by x cubed, you can't have it bigger on the bottom. So my slant asymptote is actually just y equals 3x. So if I was to graph this on Desmos, again, I have not graphed this yet, but I know it has an intercept of 0, up 3 over 1, so this is my slant asymptote. So as it goes off to infinity, somehow it's going to do something like this, something like this. It could be on either side, but it's approaching that slanted line. Let's look at this last one. This was also a slant asymptote because you can notice, if you can get through all this writing, you can notice that the degree of the top is 3 and the bottom is 2. So if the degree of the top is bigger, you'll long divide. So x squared plus 0x plus 1 divided by x cubed plus 0x squared plus 2x plus 2. So we'll divide these, x cubed divided by x squared, which is x. And then I'll multiply that to these three. So x cubed plus 0x squared plus 1x. Then I have to subtract, so I have to change the signs. These were all positive, so they all become negative. So x cubed minus x cubed goes away. There's 0x squared. This becomes x. But I can't divide x by x squared because it's already smaller. So again, this one's a pretty straightforward. The slant asymptote is just y equals x. Now most of the rationals we'll definitely use the horizontal where they'll be equal or the degree bottom. Those are what we typically will call proper rational functions. But there are some that you'll see, and we've seen some that kind of go off in a slanted way. That's the way those work.